With a project as complex as Becca, it can be difficult to know where to start. This tutorial is a Hello World type introduction. By the time you're done with it, you'll have a minimal working example that you can use as a starting point for whatever final application you like. Reinforcement learning benchmarks, simulated robots, or for the very bold, physical robots. You can think of Becca as a brain. To do anything interesting, a brain needs a body to run and an environment to run it around in. Together, the body and the environment we'll call the world. Becca tries to be a solution to the reinforcement learning problem. That means that it operates in discrete time steps. At each time step, it accepts a set of sensor values and a reward value. It also returns a set of actions. Each world might have a different number of sensors and expect a different number of actions. These need to be defined within each world. Becca is unusual among reinforcement learning algorithms in that it can accept pretty much anything as a sensor value. A floating point number, an integer, a string, or any other type that can be turned into a string. The actions that Becca returns are floating point numbers between 0 and 1. It's up to the world to decide how to interpret these and what response they precipitate. The reward value is a floating point number between -1 and 1. Positive values are desirable, negative values are interpreted as punishment, +1 is the largest reward possible. -1 is the worst punishment imaginable. To show how this works, we'll create a simple world, connect it up with Becca, and run it. I assume that you've already installed Becca, but if you haven't, you can follow the quick start download in Becca's README or the installation for developers in Becca's wiki. The links are below. If you'd like to download the Hello World example file, there's a link below for that too. I'll step through the code here line by line to show what's going on. First, we import NumPy because it gets used a lot. And then we import Becca.brain and the Becca.baseWorld. BaseWorld is a shell of a class that provides some solid defaults. It's convenient to create the world as a class. In this particular world, we'll have one sensor. The world will assign it either the value of cat or dog. It will be Becca's job to choose whether it belongs to the cat or dog category. This is analogous to an image recognition task where the algorithm is tasked with sorting images into a cat or dog category. But to keep this example as simple as possible, we'll reduce it to a string recognition task. The visualize interval shows how often, in time steps, to give a snapshot of the world's state. And then, most importantly, we initialize the number of sensors and the number of actions in our world. In our case, we have a single sensor, which can have one of two values, cat or dog, and we have a single action, which allows Becca to choose between them. These two variables, n sensors and n actions, are necessary for Becca to be able to talk to the world. We also initialize the list of sensors with an empty string. The next thing we need to do is to create a method called step. This advances the world by one time step. It takes in the most recent action and returns a new set of sensor and reward values. Here we specify how the action will be interpreted. Any value above 0.7 will be counted as a vote for cat. If it's above 0.4 or less than or equal to 0.7, it's a vote for dog. And if it's below 0.4, it's a vote for neither. We increment the world's own time step variable by 1. We didn't initialize it above, but it was initialized in the base world module. Then we add the logic that interprets the action as a vote for cat, dog, or nothing. After that, we compare Becca's guess with the last recorded value of the sensor. If the guess is correct, the reward is 1. If the guess is incorrect, the reward is -1. And if there's no guess, the reward is 0. To give us an occasional snapshot at what's happening inside the world, we check whether the time step is a multiple of visualize interval. If it is, we generate a brief report and show it at the console. Then, however this time step played out, the world generates a new sensor value. It has a 50% chance of being a cat or a dog, independent of what happened on the previous time step. Finally, we create the if name equals main block so that if our hello world.py module is run as a script, it automatically connects the world to Becca and runs it. When we run it, this is what we see. First, Becca looks for a saved version of itself that has trained on our hello world. It can't find one, so it starts fresh. We also get an initial snapshot at time step 0 before any sensor values have been assigned and any actions have been taken. Then we get notifications that a reward history image has been saved and that a brain activity image has been saved. We can go open these up and get a sense for how Becca is doing. Looking at the reward history for our hello world brain shows that by the time Becca has completed 2,000 time steps, it has learned pretty well how to choose between a cat or a dog string. After that, its performance settles in and flattens out. Two things about this are odd. The first is that it takes more than 1,000 time steps for Becca to learn how to do this trivial task. Simpler reinforcement learning algorithms would be able to learn it almost immediately. This difference is due to the fact that Becca is intended to be a general purpose brain. Because it's prepared for so many different types of worlds and so many different types of patterns, it's actually much less efficient at learning trivial ones. This is not worrying. Becca is not designed to perform perfectly on simple tasks or toy problems. It's intended to perform passably well on a wide variety of complex problems. This leads us on to the second thing. As time goes on, Becca's performance actually gets worse, at least up to a point. At 2,000 time steps, it's getting a reward of 0.7 on average. That means that more than 3 times out of 4, it's guessing correctly. But as time goes on, that reward drops below 0.5. This indicates that it's only guessing right about half the time. This is another manifestation of the fact that it's designed to do a pretty good job on lots of different hard problems rather than a perfect job on a small set of simple problems. If we open up a brain activity image, we can get a snapshot of what's going on inside of Becca while it's performing this task. We can start by looking at the sensor. There's only one, so it's sensor number 0. It can handle both numerical and categorical or string inputs. But we've only given it string inputs. It's learned that there are 2 different types of input, cat and dog. On this particular time step, the sensor had a value of dog. Becca also shows its previous actions. These represent choosing the cat category and choosing the dog category, or an action value of 1 or a value of 0.5. Here, Becca shows that on the previous time step, it selected dog, represented by the copper line. The discretized sensors are called inputs, and the discretized actions are called commands. The inputs and commands are also passed through a sparse clustering algorithm called a zip tie. We won't discuss it in more depth here. I'll save that for another tutorial. We can understand what's going on in the hello world without digging into it yet. The commands, inputs, and zip tie values are all passed as features into the model. Becca uses sequences of features, goals, and outcomes, analogous to state-action-state models, to learn how to navigate its world. It has curiosity about each combination of features and goals that drives it to learn what happens when it takes a certain action in a given situation. It learns to associate reward with each combination of features and goals. That is, it learns what actions in a given situation tend to be the most rewarding. In this plot, copper dots show a positive expected reward and turquoise dots show an expected punishment or a negative reward. Here we can see the feature row associated with the dog value of our sensor and the expected reward associated with guessing cat and guessing dog. As we would expect, the reward for guessing cat when the sensor says dog is negative. And of course, the reward for guessing dog when the sensor says dog is positive. Learning this pattern has helped Becca reach the high performance levels that it has. This plot also shows the previous feature goal pair, the prefix, which shows the dog feature being active and the dog selection being made on the previous time step. It also shows the expected outcome. For each goal that Becca could possibly choose, it shows what it expects the features to be in the next couple of time steps. Because our world changes randomly at each time step, there is very little structure to this plot. The two-dimensional plot here is actually a collapsed version of the full feature goals and outcomes three-dimensional array. This is how Becca represents its complete model of the world. The expected reward associated with each goal is added up across all the features. The expected curiosity that would be satisfied by each goal is also added up. The expected reward from fulfilling any goals that were carried over from previous time steps is also added in. And the goals from the previous time step are shown. Behind the scenes, a new goal is selected, and then the goal set is updated to include that new goal. In this case, the goal is to choose the category dog, comma. This is the second command from the left. Because this new goal is associated with a command, it can be issued immediately on the current time step, which it is. This is represented by the turquoise line on the choose dog command. While this overview isn't deep enough to offer a full explanation for how Becca works, I hope that it's been enough to show how to take a world and let Becca learn how to control it. Good luck. I look forward to hearing how it goes for you.